Hello, welcome to my talk. Thank you very much for coming. I'd like to thank the organizers for allowing me to speak here. It was very much a last-minute affair for me. I saw a post on LinkedIn by Cherry saying, oh, there's one day left before the deadline. So it was a bit of a mad scramble to put a proposal in. And I'm glad to say that I put together something which I think is pretty relevant for PyData. Although, a few years ago I might have thought that perhaps this wasn't something I knew anything near enough about. So a little bit about me first. So I'm a research software engineer on the DataSig project, which is a joint project between the University of Oxford, UCL, Imperial, and the Alan Turing Institute. And basically our mission, if you call it that, is to bring signature methods and rough path theory to people in the data science community and people doing time series analysis, anything that involves paths. And we'll see in a little while that my definition of path might be not necessarily things that you expect. So I call myself a Python enthusiast. I started programming Python when I was a PhD student a long time ago. But I'm a pure mathematician at heart. I did a PhD in pure mathematics. I lectured pure mathematics for a short while. And then somehow I ended up teaching Python. And as part of that, I went to PyCon UK, and I found out about these wonderful jobs called research software engineers. Highly recommend to anybody who might be so inclined. It's very good fun. It's like the perfect matchup between my nerdy maths side and my nerdy programming side. It's the perfect storm. I also wrote a book, which was also something I wasn't expecting to do. I'm not going to talk about it, but it's called Applying Math in Python. The math bit really still bothers me today. I'm British, so maths is the correct pronunciation. But we won't go into that anymore. And as I said, I was formerly lecturing pure mathematics, or mathematics in general, at a couple of universities for a little while. And I thought this was a really nice place to start because in a really, really roundabout kind of strange way, this is really the start of my story when it comes to analyzing time series. So back in 2017, I know, the pre-times, I was lecturing at Nottingham Trent University in a sort of gap period where I weren't sure what I was going to do. And I was asked to supervise some third-year dissertation students. And one of them was a very good student who was a financial maths student, actually, not a pure mathematician. But because of the reasons I was in this job, they'd asked me to carry on with supervising. So I said, yes, no problem, I'll do that. And after a little bit of discussion, after a meeting or two, we decided that, she decided that she'd like to understand how events in the world have an effect on stocks, on prices, on anything in general. So this was all about how you take some kind of information about the world and predict what might happen in the stock market or anywhere else. And this was really interesting. Unfortunately, being a pure mathematician, I know absolutely nothing about stock option pricing or how to actually deal with these things. I'd done a little bit of statistics dealing with time series data when I was a bachelor's student many years prior. Oops. Sorry, Snapcraft being a bit disagreeable there. But I really didn't know anything anywhere near enough to really do this student justice. And I'm not saying that this student didn't do well. She did very, very well. What she produced was very, very good and reflective of the work that she put in. But from my side, I felt that I let this student down because I could have given her way more information about this if I'd known then what I know now. So this is an exercise in hindsight, really. So what is it that I should have known then that I know now? And the answer to that question is controlled differential equations. So broadly speaking, a controlled differential equation is something where you take in some kind of information about the world, a path that describes some events that are happening in the world, and you try to predict the response to that input path, that control. So here, my input signal is x, xt, it's a path. It's something that depends on some time parameter, or actually it doesn't have to be time parameter, but it informs some kind of variability in a system. And from that, I generate an output signal, my y of t. And usually it has some formal relationship defined by this equation. So what this is saying is that the small increments of y depend on some function of y and the small increments of x. And that sounds horribly complicated, and it is. And I don't claim to understand this theory at all. But luckily, my supervisor at Oxford, Terry Lyons, literally invented this field of mathematics. So he knows a lot about it. Unfortunately, I can just implement the things he sends my way, and this is a very good relationship, I think. So it turns out that the result, the solution of this kind of differential equation ends up being determined by an important construction which depends on the input path x, and that is called the signature of the path. And really what this is an abstract summary of the variability of the path that you take in. I'm not going to go into any more detail about controlled differential equations, so you can breathe a sigh of relief. This is a very deep and very mathematical topic. I don't need to go anywhere near as deep into that. But I am going to go into signatures, because signatures are definitely more interesting to this crowd. So what is a signature? Well, I said before, signature is an abstract description of a path, and it lives in this horrible, scary space here, the tensor algebra. But what this is saying, really, is I have some information at lots of different levels. Okay, so my levels are the k's here, and each level describes an extra dimension of the variability of the path. Okay, and we'll see later that actually usually you truncate this, because obviously we can't deal with infinity in computers. That does not work. But for now, let's just pretend that this is what we have. And what we really do is we flatten all this out into one big long line. So the number in the top there inside the brackets, that is the level k. And this is indexed by words, so tensor words in a d-dimensional alphabet. Okay, so I have my first element is the 0th element. That's just a scalar, so a real number. And then I have d letters, 1 through d, rather unimaginatively, because we're mathematicians. We don't like to complicate things if we don't have to. And they're my level 1 elements. And then I have the level 2 elements, which are things like 1, 1, 1, 2, 1d, and then all the way up to dd. And I write them out in this lexicographical order, and I get this long sequence, and then finally somewhere in the ether I have the nth level, which has letters I1 up to in as my word. And this is an abstract description of the path. Well, it will be. There are more tensors of this form than there are descriptions of paths. We'll see that in a minute. So the signature of a path actually has a very special form inside this. I'm not going to go into exactly the details of this, but there is a small subset of all these possible long sequences that are actually signatures of paths. I can write down exactly what the elements are by sort of enumerating these words and writing out full. So the first term, the scalar term, is always 1, okay? And you'll see why this is relevant in a moment, but basically solutions to differential equations, going back to that for briefly, usually look like exponentials. 1 is usually at the beginning of an exponential in some way. So next, I have differences or increments in my values of each letter, okay? So these are the differences in the ith coordinate between the end point and the start point. So I'm looking over this interval a to b, and this is just the increment that occurs in the x, in the ith coordinates of x over this interval. So I have d of those. And then my second terms are double integrals, where I'm integrating over the sort of triangle that's defined between two coordinates in my path. So I'm integrating the ith coordinate of my path against the jth coordinate of my path over the sort of triangle defined between them. This is a scary-looking quantity, but it's something that we can actually compute. Okay, and we don't have to do any complicated integrals to actually compute these in real-world scenarios. And I'll come back to that in a few moments. And then we go down through all of the different levels, and we end up with this horrible iterated integral somewhere down off in the world. But the exact formulation of this doesn't actually matter so much, because computationally, there's a very convenient way of writing these things out. Okay, so as I said here, this is more for the people reading the slides later. xit is the ith coordinate of xt at time t. Okay, so just to very briefly summarize the properties of such things. So we're mathematicians, we like to prove theorems. So these are all sort of little theorems about paths. And most of them come from the form of the integrals that we've just looked at. You don't need to know anything about integration. I'm about to tell you everything that you need to know for this to work. But if you do understand, then great. Okay, so they're invariant to reparameterization. So what does this mean? It means that if I take some transformation of my time t up to some reasonable transformation, it's not going to change the values of my integrals. So the signature isn't going to change either. It's translation invariant. So if I shift the whole path up in the space, then that's not going to change anything. If I shift it down, shift it around, it's not going to change anything. It respects concatenation. So if I take my path and I split it in two, and I calculate the signatures of each part of my path, and then I take their tensor product, then I get back the signature of the whole path. This is important. This is the property which means that if I look back at my controlled differential equation, this is the thing that you need in order to solve that using signatures. And as I said before, the full signature is this infinite object, and this isn't practical for computation. So what we usually do is we truncate it at some level. So I write this as S with a superscript n, and the coordinates of the subscripts there indicate the interval over which I am computing. Okay, great. What on earth have I just been talking about? This is abstract nonsense at its finest. We're deep down Alice's rabbit hole. Right, so if I look at these things and I try and describe what the actual explanation of what all this is. You might recall that integrals give you areas under curves. Iterated integrals give you areas between two curves in the appropriate domain. So if I look at the 1-2 element of my signature, you'll notice that this is the iterated integral over the two coordinates of my path, I and j, or the 1 and 2. And what this really amounts to is actually the area above one part, but below it in the other sense, or between. This is really confusing because the components are sort of living in two-dimensional space, but your area is sort of being measured in a third sort of plane between them. Okay, so the yellow highlighted area is sort of like this integral, the value of this integral. And similarly, if I go to 2, 1, it's the corresponding bit, the bit below on this plane. Notice that my axes here are the first coordinate and the second coordinate. So first coordinate on the x-axis, second on the y-axis. So this is the plane that sort of is between these two coordinates. So these are the sort of geometrical interpretations of the values of these second-degree elements from the signature. And we can go further than this. Ignore this bottom thing. I may have borrowed this slide from a colleague who I think lots of people on my team have borrowed these slides because I got them from somebody else, not the original author, but credit to the original author. We can do a little bit more with this. So we can do some differencing here, and we end up with these bits between the curve and this diagonal line that goes between the endpoints of this curve. And these are actually quite important things. These are called Levy areas, and they are a very interesting feature because they take account of the order in which things happen. I'm not going to go too much into detail, but basically signatures only really matter, the values of signatures only really depend on the order in which events happen. And this goes back to what I was talking about at the beginning, when my student wanted to look at the effect of something, some event on market values. The order matters. If the event happens before some reaction in the market, then it's plausible that that event caused that reaction. If it happened after, then clearly it didn't have anything to do with it, although they may have had a common cause in retrospect. So these Levy areas are very important. And actually, you can reduce the complexity of your signature if you sort of strip out the redundancy, because clearly the area above and the area below, you can kind of calculate from one another. These Levy areas are sort of like what happens if you strip out all that redundancy. I'm not going to talk about that today. Notice that all of these are the property of the path and not of the points on which you sample your path. They only depend on the path that they came from. So here's a really silly way to calculate things. Suppose that I am given a sequence of increments. Okay, so these are the changes in my path over some small time interval. Then I can actually calculate the higher order terms from these, making some assumptions about what my path might look like. And then I can use these increments to calculate the whole signature, or something which approximates the whole signature. So what I do is I take these increments and I embed them in my tensor space. So the 0 coordinate here is a constant term. That doesn't play any part. The first order terms are replaced by my increments, and I set everything else to 0. And then what I do is I take this horrible product of the exponentials of all of these increments, and these are exponentials in the free tensor algebra. So they're defined as this formal power series where you take 1 plus x squared over 2 plus so on and so forth. If you're familiar with how the exponential function is defined as a power series, then it's the same form. It's just that every time you're doing a tensor product instead of or a tensor power instead of a normal multiplication. This is a well-defined object, and it gives you something which approximates the signature terms of higher order using only this first-order increment data. Okay, so I realized that was a lot. So here's a really, really silly little example. So suppose I've been given two increments. Say x1 is 1, 2, and x2 is 3, 4. Who's done an example of something where they've used these 2 points for show of hands, anyone? Yeah. It's a common thing. I love it. I've got dozens of examples of matrix algebra with 1, 2, 3, 4 in a square matrix. So, for example, these could have come from a path that I'd sampled with the point 0, 0, 1, 2, and 4, 6. Okay, so if I take the difference between consecutive things, I get these 2 increments. So what I do is I embed them in my tensor algebra, and I take their exponential. Okay, I'm just going up to level 2 here. So this is the constant term, the increments, and then this increment tensor product increment divided by 2. Okay, so these are fairly easy to work out. If you take tensor product of 2 vectors, it's the outer product. So you take the first coordinate of one times the first coordinate of the other, and that gives you the top left. If you take out these 4 last elements, this is like a 2 by 2 matrix you get if you put the vectors the wrong way round in the dot product, right? It gives you a 2 by 2 matrix, and this is the outer product of these 2. And I do this for both increments, and I get 2 values. And then I take the tensor product of these 2 things, okay? So I've written out in full here, so you can see exactly what the form of this is. So the first term is always 1. That's fine, I can do that. Then I've got my increment values. Okay, so in the tensor product, these are really added together because it's like 1 times this plus 1 times the other. And then the higher order terms are all slightly more complicated, but not much. Basically, there's 1 contribution coming from the increments and 1 contribution coming from each of the other, there's one contribution coming from each of the level 2 things on either side, and then 1 contribution coming from the 2 level 1 terms in the middle. So if you chase this through, you'll see where all the terms come from. It's tensor product. Okay, so that was the signature of a very stupid example. Why is this interesting? Well, there's a theorem that tells me that if I look at paths up to some equivalence, there's the magic words, then all of the functions that I can describe on paths, all the continuous functions, are exactly linear functions defined on signatures. In other words, anything I can learn about the behavior of a path, I can learn from the signature, and vice versa. So if I know something about the signature, I know something about the path. That might be interesting. In particular, if I take path data, so I sample data from a path, and I compute its signature, I can make inference based on the signature and not the original path data. And here's the crunch. The dimensionality of path data can be enormous. If I take a path and I sample it 1,000,000 times, then I've got 1,000,000 times the dimension of my path. But my signature over that, if I compute the signature of all those million points up to some degree, my signature has only as many points as it would have if I had 1 point. The signature is a fixed size object. So it's exponential in, it's geometric in the powers of the thing. So if I have 2 coordinates, then the signature of level D has 2 to the n plus 1 minus 1 points in it. Okay, so it's like 1 plus d squared plus d cubed, etc. This is fixed. So the number of terms in my signature does not depend at all on how many increments I use to calculate it, but it still summarizes the variability that's captured in those increments. Now, this is hugely important for anybody who's tried to put time series into some kind of machine learning or data science-y kind of algorithm, where if you try and put 1 million points in, something is going to break, or it's going to take a really long time. But even a modest depth signature could have, a few thousand points, tens of thousands of points. That's still a lot less than 1 million. So this can be used as a way to reduce the size and complexity of a data set that you then feed into a machine learning model, say. All right, so can I give you a real example? And the answer is yes. So let's take 2 paths here. So I'm going to take some paths which are handwritten digits, and I believe these are taken from the MNIST data set, if anyone's familiar with that. So these are paths, and I've flipped the axes a little bit so that they're drawn the correct way round on using Matplotlib. So the points are sort of sampled points taken from a person drawing on a graphics tablet of some description, and these are the digits, the paths that they describe. These don't look like traditional time series, but really they are, because these are sampled over a small amount of time as someone draws these characters. I would love to have given you a live demonstration of this, but I don't have the software or a graphics tablet to do this, and the trackpad on my laptop probably isn't up to it. So I get these 2 continuous paths that I can interrogate using signatures and try and understand how they are constructed. So I need to compute signatures. Obviously, I'm not going to do this by hand. I'm a mathematician, and I think the quality of a mathematician is that you've done at least 1 computation by hand that you regret doing. That's what Mathematica is for, or Maple, or whatever symbolic maths package you have. So what this really is a reasonably short sequence of values or increments in a 2-dimensional space. Okay, so these are not complicated objects, but I don't want to compute them by hand. So let's try and identify the digit 3 using a signature and not capturing anything. So I'm obviously not going to do this with just 1. I'm going to take a few of them and combine them in some way to get something that I can use to then classify. And just a little note, this is the least scientific way that I could possibly imagine to do this problem with, but it's basic and it shows the point without going too much into detail. Okay, so what my procedure is going to be, I'm going to take several digit 3s from this data set that I have. I'm going to compute their signatures. Then I'm going to compute the expected signature. So this is just the average, the mean signature over my different things. So I'm going to get a thing that looks like the signature of a 3 or summarizes in some way the signature of a 3. And I'm going to compare new path signatures of new digits that I've not seen before and see if they're also similar to 3s. Okay, so there are actually several Python packages for computing signatures. So there's eSig, II signature, and signatory. Signatory is based on PyTorch, so if you're into using PyTorch as a machine learning framework, then you can plug this straight in. And I'll show you some example code. Well, I'll tell you where to find some example code in a moment, because I don't like putting code on my slides. I'm the maintainer of eSig, and while it's not quite in the form that I'm terribly happy with at the moment, there are major updates coming. So I'm going to use eSig to do these computations, mostly because it's the only one I had installed. So there's a function in eSig called stream2sig, which takes a stream of points and computes its signature. And it just takes this as like an n-dimensional, or an n times d array. So n is the number of samples, d is the number of dimensions of my path, and it does the differencing for you, so you don't have to convert these to increments. Okay, so I'm going to take depth 8, so this level 8 signatures. So these are going to have 2 to the 9 minus 1 points in them, or in other words, 511 entries. And this is going to be my feature space, if you like. So let's actually calculate these things. So if I compute all these signatures and I take their average, this is roughly what I get, or at least this is the first few terms of what I get. Okay, so you can see the 1 at the front there, minus 0.04, 1.88, and so on. So this is an abstract summary of what I expect a 3 to look like. So what happens if I take a new path and I compute its signature? Okay, well, this is what I get when I do such a thing. And you'll notice that it's not terribly dissimilar, but there are some definite differences, particularly in these higher order terms here. So I've got really small middle second order terms, 0.84, 0.89. These don't look quite the same. And if I compute naively, their maximum modulus distance is 5.27, which is pretty large. I mean, considering the size of these coordinates that I've put up, this is quite a big difference. And in fact, they are different. This is the signature of the 6th path that I showed you on the first slide. So if I'd guessed that these were not the same based on this data, I would have been correct. Now, I'm not saying that this is a good way to classify digits. There are far better ways of doing this, but this is a very stupid way of doing it, which sort of works, and it shows you roughly what kind of things are possible. So what kinds of things are possible? Well, obviously there's handwriting recognition, and we've done quite well with this, actually, by analyzing the strokes and drawing a path. This is something that we have a good example of on our website, details in a moment. So this is from the MNIST data set, which, as I said, I think these digits were actually taken from this set as well. Then we have sepsis detection. So we use path signatures to predict sepsis in the MIMIC3 data set, which has been mentioned at least one other time this weekend. This, I believe, was part of a Kaggle or similar kind of competition, and I believe we did pretty well. Then there's human action recognition using landmark data. So we take landmark data from motion capture, and we try and classify what kind of action is being taken using signatures. Drone identification, so taking in data from radar and other things to try and detect drones and identify drones. Again, all of these with asterisks are things that we have examples of on our website. Natural language processing. Yes, sentences and paragraphs are paths in some sense, and therefore we can compute their signatures, and we can use those signatures to classify things about language. The example we have on our website is using path signatures to identify the author of works taken from the Project Gutenberg corpus of books. Analyzing data usage, so I don't have an example of this, but there is a paper which is listed on our website where we take energy data, so voltage and current, and we use this to understand energy usage in a house over a very long time. This was a very big calculation, something like 5 years of energy data. And analysis of radio frequency, which I don't think is listed on our website, but is an ongoing project that we have, looking at data from radio things. I don't remember exactly the context. So again, this is just a note for people who are looking at my slides later. So where to find out more? So this is information that can be found on our website, datasig.ac.uk. If you go to the research section, you'll see our recent preprints and a list of self-contained Jupyter Notebook examples that you can work through and see if you have any usage for these techniques. There's also our GitHub. If you take the eSig off, you'll get our sort of GitHub organization, which has all the examples mentioned above, plus some other code. That's all there. And then my personal details at the bottom, so you can reach me at maths.ox.ac.uk, my personal website and my GitHub, both in a Klein bottle. Thank you. Does anybody have any questions?
Interesting talk. One general question is, what do you think your techniques can achieve that other methods can't? What's the advantage of your signature methods compared to, say, historical methods?
So the big advantage of signature methods is that they, in my eyes, besides the theoretical things, there's one really big example, and that's this sort of size compression. And the signature is not actually the most efficient. You can actually take the log signature, which kind of throws away the redundancy. And this is an even more compact representation. But signature is a tool that one might use. So it's not like it's just a single method that you can apply in certain scenarios. It's something that you might incorporate as well as other things to improve your results or to take in time series data that you couldn't otherwise use, or to provide some extra information about the temporal effects of time series data. There are lots of different things that you can do with it that are not mutually disjoint from other things.
Cheers, thanks very much. That was a very interesting talk. I did have just one kind of question about the setup of the signatures. You mentioned that you kind of set up a truncation to some level.
Yes.
In live cases, like in real life examples, is there some way to intuitively pick that kind of level, or do you have to kind of trial and error this, or maybe, as a form of cross-validation, that kind of thing?
Yeah, so in the applications that I've worked on personally, this has been a sort of hyperparameter that we've tuned. So we would include this as part of our grid search or cross-validation randomized search. So yes, this is something that you absolutely need to play with. Higher order terms are more expensive to compute. So if you can get away with fewer terms and using lower order signatures, then that might be beneficial if you're looking to do something very quickly. if time is not a problem and you've got a lot of computer memory, then using a higher order signature might give you better results, but there will probably be a point of diminishing returns.
Cheers, thank you.
So related to that question, I was wondering if you can give us more like intuition of what the signatures mean, and so related to the question, where do we cut? So for example, if I do something like a Fourier transform, and I throw out the coefficients, I know that I'm throwing out high frequency coefficients, but here I just don't know what I'm throwing out.
Right, so a Fourier transform takes in a signal, and it takes the signal to the frequency domain. So you transform from the frequency from the signal to the frequency domain. The signature, on the other hand, is a little bit more complex than that. It's a description of the variability of the path. So it's a little bit different in terms of the way that the path is constructed. Something that I didn't talk about is exactly how this works theoretically. But basically, one can compute signatures in places where Fourier transforms would give you kind of nonsense, or wouldn't help you so much, because there are some assumptions that you have to make for Fourier transforms to be actually useful. Having said that, they're not terribly dissimilar, because, as you say, a Fourier transform is really capturing the frequencies at which some path is varying. So they're not totally dissimilar, but they're definitely very different. For example, you can't go back easily from a signature to a path. That's a difficult operation to perform. It's very easy for a Fourier series, of course.
Okay, thank you.
Signatures are a dimensionality reduction technique. As a dimensionality reduction technique, what paths would have the same truncated signature, but possibly quite different appearance?
Okay, so there are obviously paths which would have the same truncated signature as one another. So for example, if you had a path which, broadly speaking, varied in the same way in the larger sort of strokes, then its signature would look something very similar to a path where the broad strokes were the same, but there was a lot of high frequency, very small variance in the detail. Sometimes the entire signature of the path is quite short. So, for example, if you take paths where you only vary in the sort of rectilinear direction, so parallel to the axes, and you take one step in each direction, at most once, then this path, I believe, if memory serves, is completely described by its signature up to level 3. These are innovative paths, I believe, is what they're called in the literature, but I couldn't cite exactly where they appear. So, for example, those would be completely described by a signature at level 3. But you could easily imagine a path which looks like this in the sort of 10,000-foot view, but as soon as you zoom in to, a few centimeters, it looks very fuzzy. Those might have some signatures that look very similar.
Thank you very much for the talk. Very, very simple question. Do you think that signature could be used for partitioning time series, like in a clustering scenario or stuff like that? And if so, would it help with extremely large time series?
Absolutely. Yeah, absolutely. I think that one of the applications that we've been looking at is trying to detect anomalies in a long sequence of events as a time series. So we take a very long thing and we compute expected signatures over small intervals, and then we compare new intervals to the expected signature, and if they look very different, then we can say that, oh, something unusual happened in this interval. So this is a technique that we've absolutely done before. I'm not sure exactly of the success or how reliable it is at the moment, but there is definitely an example of this somewhere on our website.
Thank you for the talk. Is it correct to think of signature as a pre-processing step? And then once I have the signatures, I can apply different, for example, machine learning models
Absolutely.
based on the problem. But I'm wondering if there are models that are more, that matches better to this particular type of pre-processing.
I don't know of a model where the signature would work especially well. I know that we've used it with great success in combination with tree-based models, LGBM specifically. So there are certainly some models which are tried and tested, so to speak, but I'm not aware of any reason why you couldn't just plug this into anything. I know that people have run this through torch neural networks with success as well. So I wouldn't want to say definitively, but I could imagine that there are models where this kind of isn't the right thing to do, perhaps. Sorry, I can't give you a more concrete answer. Yep.
Is it practical to put priority on more recent data and use signatures at the same time?
Yeah, so you could, for example, take signatures over rolling windows and weight them according to how recent they are. For example, that might be something you could do. Of course, it depends entirely on what you're trying to model or classify, or what your global task is. But absolutely, you can compute signatures of rolling things. The signature actually is a path itself, just in a much bigger dimension than the original path. So.
Thank you very much, Sam.